Null and alternate hypothesis.
The null hypothesis states that there is no change or difference in the group means. It is based on the notion that any change from the past is due entirely to random error.
We are saying that the population value has not changed from one time to another, or the sample statistic does not vary significantly from an assumed population parameter. One sample.
The mean brand preference score of male teachers aged 35 to 40 is 85.
Two samples.
There is no difference in the mean brand preference score between male and female teachers aged 35 to 40. The alternate hypothesis, or sometimes called the research hypothesis, is the hypothesis that contradicts the null. It is commonly written as HA. The alternative hypothesis can indicate the direction of the differences or relationship, or assume a neutral position.
If direction is emphasized, indicated in the alternative hypothesis, we called it one-tailed test.
Otherwise, the test will be a two-tailed test.
The following are examples of alternate hypothesis.
One sample.
The mean brand preference score of male teachers aged 35 to 40 is not equal to 85.
Two samples.
There is a difference in the mean brand preference score between male and female teachers aged 35 to 40.
Directional and non-directional hypothesis.
Hypothesis can be stated as directional or non-directional. This indication is reflected in the alternate hypothesis. If you use terms like more than, less than, positive or negative in stating the relationship between two groups or two variables, then these hypotheses are directional.
An example of a directional hypothesis would be: the greater the stress experienced on the job, the more likely an employee scouts for another job.
Another way of stating a directional hypothesis is the if-then approach. If employees are given more safety training, then they will have fewer accidents. Non-directional hypotheses postulate a difference or relationship but do not indicate a direction for the differences or relationship.
We may postulate a significant relationship between two groups or two variables, but we are not able to say whether the relationship is positive or negative.
An example of a non-directional hypothesis would be: there is a relationship between stress experienced on the job and the likelihood an employee will search for another job. Another example of a non-directional hypothesis is: there is a relationship between job commitment and the likelihood to search for another job.
There is a relationship between job commitment and the likelihood to search for another job.
Sample statistics versus population.
Inferential statistics help us make judgments about the population from a sample. Sample statistics are summarized values of the sample and are computed using all the observations in the sample.
Population parameters are summarized values of the population, but they are seldom known. This is the reason we use sample statistics to infer on population parameters.
A null hypothesis refers to a population parameter, not a sample statistic.
Based on the sample data, the researcher can reject the null hypothesis or accept the alternative hypothesis whether there is a meaningful difference between the groups or there is no meaningful difference.
In the latter case, the researcher would not be able to detect any significant differences between the groups. It is important to understand that while the null hypothesis may not be rejected, it is not necessarily accepted as true.
The null hypothesis typically is developed so that its rejection leads to an acceptance of the desired situation.
The alternative hypothesis represents what we think may be correct.
In statistical terminology, the null hypothesis is notated as HO, and the alternative hypothesis is notated as HA.
If the null hypothesis, HO, is rejected, then the alternative hypothesis, HA, is accepted.
The alternative hypothesis is the one you must prove. Self-check 9.2.
Explain the difference between sample statistics and population parameters.
Type I and type second errors.
The assumption that there is always a risk of inference when a researcher studies a population may be incorrect.
Thus, in research, error can never be completely avoided, and statistical tests that the researcher performs to accept or reject the null hypothesis may be incorrect.
Researchers, therefore, need to be aware of two types of errors associated with hypothesis testing: type I error and type the second error.
Type I error.
Type I error, referred to as alpha A, occurs when the sample results lead to rejection of the null hypothesis when it is true.
The probability of this type of error, also referred to as the level of significance, is the amount of risk regarding the accuracy of the test the researcher is willing to accept. Thus, the level of significance is the probability of making an error by rejecting the null hypothesis.
Depending on the research objectives and situation, researchers typically consider either less than 0.05 or less than 0.1 as an acceptable level of significance.
The researchers are willing to accept some risk they will incorrectly reject the null hypothesis, but the level of risk is specified before the research project is carried out. If the research situation involves testing relationships where the risk of making a mistake is high, the researcher would specify a higher level of significance, for example, less than 0.1.
In examining the relationship between two chemicals that might explode or the failure rate of an expensive piece of equipment, the researcher would not be willing to take much risk.
On the other hand, when examining behavior relationships or when the risk is less costly, then only the researcher is willing to take more risk. In some situations, the researcher may even accept a 0.10 level of significance.
Type second error.
The second type of error is referred to as type the second error. Type the second error occurs when, based on the sample results, the null hypothesis is not rejected when it is, in fact, false.
Type second error is generally referred to as beta B error.
Usually, the researcher specifies the alpha error ahead of time, but the beta error is based on the population parameter, mean or proportion, and/or of the sample size.
A third important concept in testing hypotheses for statistical significance is the statistical power of the test. The power of a test is the ability to reject the null hypothesis when in fact the null hypothesis is false.
The statistical power of a test can be described as 1. B. The probability of correctly rejecting the null.
The probability of a type the second error is unknown, but it is related to the probability of a type I error. Extremely low levels of type I error, A, will result in a high level of type the second error, B, thus it is necessary to reach an acceptable compromise between the two types of error.
Sample size can help control type I and type the second errors. Generally, the researcher will select the sample size in order to increase the power of the test and to minimize type I error and type the second error.
The trade-off between type I and type the second errors has a practical dimension as defined by the costs incurred for each error. Often a change in the status quo is associated with a great cost, the risks or gambling the future of the firm on a new technology, a new investment in an equipment, etc. Since the change must be beneficial, the risks associated with alpha should be kept very low.
However, if it is essential to detect changes from a hypothesized mean, the risk of a beta would be more important.
Thus, a higher, less critical alpha level would be chosen.
Steps in hypothesis testing. The steps in hypothesis testing.
State the null and alternative hypothesis. Make a judgment about the sampling distribution of the population and then select the appropriate statistical test, based upon whether you believe the data is parametric or non-parametric.
Decide upon the desired level of significance, p equals 0.05, 01, or something else.
Collect data from a sample and compute the statistical test to see if the level of significance is met.
Accept or reject the null hypothesis.
Determine whether the deviation of the sample value from the expected value would have occurred by chance alone, 5 times out of 100.